Guidance for inspectors, on-stream and off-stream inspection of spherical tanks and pressure vessels, best practices for safe and effective equipment inspection. On-stream and off-stream inspection of spherical tanks, purpose of this presentation. The primary purpose of this presentation is to provide inspectors with clear, practical guidance for performing both on-stream and off-stream inspections of spherical tanks and spherical pressure vessels. It aims to bridge the gap between code requirements and day-to-day inspection practice by explaining not only what must be inspected, but also why certain inspection activities are important and how they should be carried out. The presentation emphasizes consistency in inspection planning, execution, and reporting, which is essential for long-term integrity management. Another objective is to help inspectors recognize common damage mechanisms associated with spherical vessels and to align inspection methods with those damage mechanisms. By understanding the intent of API 570 and API 572, inspectors can better prioritize inspection areas, select suitable non-destructive examination techniques, and determine appropriate inspection intervals. The presentation also supports improved communication between inspectors, engineers, and operations personnel by establishing a common technical understanding. Ultimately, the goal is to support safe, reliable operation of spherical tanks, minimize the risk of leaks or failures, and ensure compliance with applicable industry codes and standards while applying sound engineering judgment. Applicable codes and standards. What is a spherical tank? Common design features. Inspection of spherical tanks and pressure vessels is governed by a combination of in-service inspection codes and construction standards. API 570 provides the overall framework for in-service inspection, rating, repair, and alteration principles, which, although originally focused on piping, are widely applied in pressure equipment integrity programs. API 572 offers detailed guidance on inspection practices, inspection planning, damage mechanisms, and inspector responsibilities, making it a key reference for both on-stream and off-stream inspections. ASME codes, particularly ASME Section 8, establish the original design, fabrication, and pressure rating requirements for pressure vessels, which form the baseline against which in-service condition is evaluated. Inspectors must understand how these codes interact. ASME defines what was built, while API codes define how it is inspected and maintained in service. Knowledge of additional standards, such as ASME PCC 2 for repairs and API 579 for fitness for service assessments, is also important. Effective inspection requires not only awareness of code requirements, but also an understanding of their intent, limitations, and the need for engineering judgment when real-world conditions differ from ideal design assumptions. A spherical tank, also referred to as a spherical pressure vessel, is a vessel designed with a spherical shell geometry to store pressurized liquids or gases. The spherical shape provides uniform stress distribution under internal pressure, making it one of the most efficient pressure vessel configurations. These tanks are commonly used for storage of LPG, ammonia, butane, propane, and other pressurized or refrigerated products. Spherical tanks typically consist of multiple shell plates welded together, supported by columns or a skirt structure that transfers the load to foundations. They include various nozzles, manways, and attachments for process connections, instrumentation, and safety devices. While the spherical geometry offers mechanical advantages, it also presents inspection challenges due to elevated heights, complex support structures, and insulation systems. Inspectors must be familiar with the design features and service conditions of spherical tanks to effectively assess their condition and identify areas susceptible to damage. Understanding the basic configuration is essential for proper inspection planning and safe execution of inspection activities. Spherical tanks are characterized by several key design features that influence inspection activities. The primary component is the spherical shell, fabricated from curved plates joined by full penetration welds. These welds are critical inspection locations due to their role in pressure containment. Support systems typically consist of multiple columns or legs attached to the shell, often with reinforcing pads, which are highly susceptible to corrosion and stress concentration. Nozzles and manways penetrate the shell and introduce geometric discontinuities that can be prone to localized corrosion, fatigue, or cracking. Many spherical tanks are insulated to control temperature or prevent condensation, which increases the risk of corrosion under insulation, particularly at supports and low points. External coatings and fireproofing systems are also common and must be assessed for condition and effectiveness. Inspectors must understand how these features interact with operating conditions, as design details often dictate where damage is most likely to occur and which inspection methods are most effective. Typical damage mechanisms, role of the inspector. Inspection planning, on-stream inspection definition, objectives of on-stream inspection. Effective inspection begins with thorough planning. Inspectors should review design and construction data, including materials, thickness, weld details, and original design pressure and temperature. Operating history, including normal conditions, upsets, and previous incidents, should be evaluated to understand potential damage drivers. Past inspection reports provide valuable information on corrosion rates, known problem areas, and previous repairs. Based on this information, inspectors can identify likely damage mechanisms and define the scope, methods, and locations for inspection. Planning should also consider access requirements, safety precautions, and coordination with operations and maintenance personnel. For on-stream inspections, limitations in access and inspection techniques must be recognized, and conservative assumptions may be required. A well-defined inspection plan ensures efficient use of resources and improves the likelihood of detecting relevant damage. On-stream inspection refers to inspection activities conducted while the spherical tank remains in normal operation, without depressurization or entry. This type of inspection is essential for monitoring equipment condition between shutdowns and for identifying developing issues at an early stage. On-stream inspections typically rely on external visual examination, limited non-destructive testing such as ultrasonic thickness measurements, and review of operating data. While on-stream inspection cannot replace the depth of examination possible during shutdown, it plays a crucial role in maintaining continuous oversight of vessel condition. Inspectors must understand the limitations of on-stream inspection and ensure that findings are interpreted within the context of reduced access and measurement coverage. When properly planned and executed, on-stream inspections contribute significantly to risk reduction and operational reliability. The main objectives of on-stream inspection are to verify that the spherical tank remains safe for continued operation and to detect any visible or measurable deterioration that could compromise integrity. Inspectors aim to identify leaks, coating failures, distortion, or other abnormal conditions that may indicate underlying damage. Monitoring corrosion rates through periodic thickness measurements allows inspectors to track wall loss trends and predict remaining life. On-stream inspection also provides an opportunity to verify that operating conditions remain within design limits and that safety devices are functioning as intended. By identifying issues early, corrective actions can be planned and scheduled in a controlled manner, reducing the likelihood of unplanned shutdowns or failures. These objectives support proactive integrity management and informed decision-making. On-stream visual inspection, on-stream thickness monitoring, on-stream CUI, and process review. On-stream visual inspection is the most fundamental inspection activity and should be performed regularly. Inspectors should examine the external shell for signs of corrosion, coating degradation, bulging, or distortion. Particular attention should be given to weld seams, nozzles, manways, and areas around supports where stress and corrosion are more likely. Evidence of leakage, such as staining, frost formation, or product odors, must be investigated promptly. The condition of insulation, fireproofing, and protective systems should also be assessed, as damage to these systems often leads to accelerated corrosion. Visual inspection of supports and foundations can reveal settlement, cracking, or corrosion that may affect overall stability. Thorough documentation of visual findings, including photographs, enhances trend analysis and future inspection planning. Ultrasonic thickness measurement is commonly used during on-stream inspections to monitor wall loss in accessible areas. Inspectors should select measurement locations based on known or suspected corrosion patterns, such as low points, areas near nozzles, or previously thinned locations. Consistency in measurement locations is important for reliable corrosion rate calculations. Measurements should be compared against minimum required thickness values to assess remaining life. While coverage is limited during on-stream inspection, trending data over time provides valuable insight into corrosion behavior. Inspectors must ensure proper surface preparation and instrument calibration to obtain accurate readings. Any unexpected or accelerated wall loss should trigger further investigation or adjustment of inspection intervals. Corrosion under insulation is a significant threat to spherical tanks, and on-stream inspections should include targeted checks where possible. Inspectors should focus on insulation damage, water ingress points, and areas around supports, nozzles, and penetrations. Limited insulation removal may be justified in high-risk locations. In parallel, inspectors should review process conditions, including operating pressure, temperature, and any recent upsets or excursions beyond normal limits. Changes in process chemistry or operating severity can significantly influence corrosion rates and damage mechanisms. Reviewing relief valve activations and abnormal events helps identify potential overstress or fatigue concerns. Integrating visual observations with process data allows for a more comprehensive assessment of vessel condition during on-stream inspection. Off-stream inspection definition and objectives, pre-shutdown preparation. Off-stream inspection is performed when the spherical tank is taken out of service, depressurized, cleaned, and made safe for inspection. This inspection regime provides the highest level of access and allows for comprehensive examination of both external and internal surfaces. The primary objectives are to confirm mechanical integrity, detect hidden or advanced damage, and establish accurate data for remaining life assessment. Off-stream inspections enable the use of a wider range of non-destructive examination techniques and more extensive thickness measurement coverage. They also allow inspectors to directly observe internal conditions, deposits, and corrosion patterns that cannot be assessed during operation. Findings from off-stream inspections form the foundation for long-term integrity planning, repairs, and re-rating decisions. Successful off-stream inspection depends heavily on thorough pre-shutdown preparation. Inspectors should review previous inspection findings, corrosion data, and outstanding recommendations to define inspection priorities. An inspection plan should be developed detailing inspection locations, NDE methods, acceptance criteria, and safety requirements. Coordination with operations, maintenance, and safety personnel is essential to ensure proper isolation, cleaning, and gas freeing of the vessel. Scaffolding, lighting, and access provisions should be planned in advance to avoid delays. Pre-shutdown planning also includes ensuring that qualified personnel and calibrated equipment are available. Proper preparation maximizes inspection effectiveness and minimizes downtime. External and internal visual inspection, thickness measurement and advanced NDE, inspection of supports and foundations. During off-stream inspection, external visual examination should be more detailed than on-stream inspection, with insulation removed as necessary to assess shell condition. Inspectors should closely examine welds, nozzles, attachments, and supports for corrosion, cracking, or deformation. Internal visual inspection allows direct observation of corrosion patterns, pitting, erosion, deposits, and mechanical damage. Lighting and access must be sufficient to ensure full coverage. Internal findings often provide valuable insight into damage mechanisms and corrosion drivers. Inspectors should document the extent, location, and severity of observed damage, as this information is critical for accurate assessment and future monitoring. Off-stream inspection allows for comprehensive thickness measurement surveys using grid-based ultrasonic testing to identify general and localized thinning. Data from these surveys should be analyzed to calculate corrosion rates and determine minimum remaining thickness. Advanced NDE methods such as radiographic testing, phased array ultrasonic testing, magnetic particle testing, and dye-penetrant testing may be applied to assess weld quality and detect cracking. Selection of NDE methods should be based on expected damage mechanisms and material properties. Proper interpretation of NDE results requires qualified personnel and an understanding of method limitations. The data collected during off-stream inspection provides a robust basis for integrity assessment and decision-making. Supports and foundations are critical components of spherical tanks and must be thoroughly inspected during shutdown. Inspectors should examine support columns, base plates, anchor bolts, and concrete foundations for corrosion, cracking, or settlement. Corrosion at the interface between steel and concrete is common and can significantly reduce load carrying capacity. Alignment and plumbness of supports should be checked to identify distortion or uneven settlement. Damage to supports can introduce additional stresses into the shell and compromise overall stability. Findings related to supports often require prompt engineering evaluation and, if necessary, repair or reinforcement. Assessment of findings and repairs, fitness for service, reporting, and summary. Inspection findings must be systematically evaluated against acceptance criteria defined by applicable codes and engineering standards. Measured thickness values should be compared with minimum required thickness to determine acceptability and remaining life. Detected defects such as corrosion pits, cracks, or weld flaws should be assessed for severity and potential impact on integrity. When repairs or alterations are required, they should be designed and executed in accordance with recognized standards such as ASME PCC 2, using qualified procedures and personnel. Post-repair inspection is essential to verify repair quality and effectiveness. Clear documentation of assessments and repair actions ensures traceability and supports future inspections. When inspection findings exceed code limits but continued operation is desired, a fitness for service assessment using API 579 methodologies may be performed. This assessment evaluates whether the vessel can safely operate under defined conditions and may establish operating limits or monitoring requirements. Inspection reports should clearly document scope, findings, measurements, assessments, and recommendations, serving as an official record for integrity management and regulatory compliance. Common inspection pitfalls, such as incomplete coverage or poor documentation, should be avoided through disciplined practices and continuous improvement. In summary, effective on-stream and off-stream inspection of spherical tanks relies on sound planning, thorough execution, adherence to codes, and informed engineering judgment. These practices collectively support safe, reliable, and compliant operation of critical pressure equipment.